last time on Friday, I talked about how to find absolute extrema, relative extrema, just to give you a quick reminder in case that you didn't watch the video, and hopefully you did. But the point is that when you find absolute extrema, you need to find the candidates for this. And we have a theorem, the stream value theorem, that says that if you have a continuous function on a closed interval, it will have a maximum, it will have a minimum on that interval. Okay? How do you find it? Well, there's a statement. Actually, I'll give you steps in here. So to find those maximum and minimums, what you do is you list your candidates, and as we saw in the previous class, you know, if you want to find relative extrema, you have to look at critical points. And the candidates for absolute extrema on a closed interval are the critical points and the endpoints of the interval. Okay? So you find all the critical points of the function, write down also the endpoints of your interval, and then all you have to do is plug in. Plug in each of these numbers in your function, whichever is the highest as your maximum, whichever is the lowest as your minimum. That's it. So if you can find critical points, you're good with this type of problems. And I did 3 examples. You know, just find your critical numbers, always throw in your endpoints, plug in, and then smallest one is your minimum, highest one is your maximum. So we did several of those. Keep in mind, there's one example here in which, remember, maximum and minimum is only one, the value, but the location could happen at different places. Like in this problem, the minimum is -3/2, but we found it at 2 different places, okay? At 2 values, at 7 pi over 6 and 11 pi over 6, you were getting those values, okay? Understand that the minimum itself is this number, the y value, but the location is the x value, okay? Could be multiple locations with the same minimum. For example, you know, think about a picture that looks like this. But let me do something that is, and imagine that these 2 guys are at the same level, right? So those 2 are minimums, but then, you know, the value will be the same, the y value, but the location is different because they happen at different x's. You understand this? So the same thing with maximum, of course, will happen. All right, so that's how you find absolute extrema, and then for relative extrema, you know, I talked about the first derivative test. And, you know, the point is at first we talked about monotony, and we have been saying this many times. We just formalized on Friday that says if you want to know when a function is decreasing or increasing, you just have to look at the sign of the derivative, of the first derivative, okay? First derivative positive means the graph is going up. First derivative negative means the graph is going down. So here in this problem, this is the sign chart of the derivative, okay? And then, you know, as I was saying, when you draw the little arrows, just follow the arrows with your finger and you will know exactly what the point is. For example, here your graph is going down and then goes up. So what sort of point do we have there? That would be a minimum, which is doing this. Do you understand this? Here, the function is going up and then it goes down. So what do we have here? Maximum. The maximum, so that's a relative maximum or local maximum. That's what the first derivative test says. Okay? If the derivative changes from negative to positive around a point, that's a relative minimum. If it changes from positive to negative, that's a relative max. But instead of memorizing that statement, just follow the arrows, and it will tell you exactly what it is. Okay? So it's easier to remember. So that brings another question. Do you know how to solve nonlinear inequalities? Because all of these problems, eventually, you're going to have a function that's nonlinear, like this, and then you will need to decide when is this positive, when is this negative. And this is a polynomial, but sometimes, I think I did other type of examples here, right? You're going to have like expressions like this with radicals and so on, and you have to be able to decide when something like this is positive, when something like this is negative. In pre-calc, you learn how to solve nonlinear inequalities for polynomials and rational functions. But the point is that the idea that you did there, you can extend it to any other function. Every time that you want to figure out when a function is positive or negative, what you do is find the zeros of the function and find the values that make it undefined. Okay? Once you find, for example, in this case, the zeros are plus or minus 2 square root of 2, because that's the zeros at the top, and then the values that make it undefined are plus or minus 4. Okay? It turns out for this problem that the plus or minus 4 are the endpoints of the interval, just because the domain of the function is this. Because the function is not defined anywhere else. Okay? But if it was defined for other points, then you will need to include 4 and -4 as part of the number line. But in this case, they are just the endpoints. So once you put all of those numbers on the line is split into different intervals. All you have to do is pick a number inside each interval, plug it into the function, the one that you're analyzing the sign, in this case the derivative, and record here whatever sign you get. If you get a negative, then you put a negative. If you get a positive, then you put a plus. And what happens is that inside that interval, the function is going to have that same sign, and this is because of continuity. Okay? Because the only way that a continuous function can change the sign is if it has a 0 or maybe value that makes it undefined because you may have an asymptote or something like that. Okay? But if it's continuous, you have to go through the x-axis by the intermediate value theorem, right? But you don't have to worry about all those theorems. It's just a very simple process. Find the zeros, value that make it undefined, write them in a line. There will be a bunch of little intervals, pick a point, plug in, pick a point, plug in, and then you don't care about actually the value. You care about the sign of the result. But here, if you see, for example, I pick here -3, and you plug it in, here I get a negative, here I get a positive, so that's negative times positive, and the bottom is always positive, over positive. What's the overall sign of this? When you do something like this, it's a negative. You understand that? That's what I put here, negative. And keep playing the same game for every little interval. Okay? Because we're going to continue doing this today. For example, what type of point is this for the function? This is the sign of the derivative of the original function. What type of point is this? Yes, but what is it? Classify it. Yeah, tell me what it is. Is it a maximum or a minimum?
Minimum.
It's a minimum. It's a relative minimum. How about this one?
Maximum.
It's a relative maximum. That's the first derivative test. You understand this? You just follow the arrows, and it will tell you exactly what it is. Okay, so let's do a couple more examples, because last time this was the one that I was doing, and I think the video cut here is lacking, and then this never showed up in the video, like the explanation of the stuff that I was saying. But now you understand exactly how to do this. Okay? Remember your candidates for relative extrema, you find the values that make the function undefined, the derivative undefined, and 0. In this case, these are your candidates. And then if you want to classify them, you need to do a sign analysis of the derivative, because that's what the first derivative test tells us. So again, the zeros at the top, that's 0, zeros at the bottom, plus or minus 2, because that's what makes them undefined. And then start, picking values, and then you do the sign analysis of each interval. So this guy is a minimum, maximum, minimum. Do you understand this? Okay. And moreover, the function, where is it increasing? It's increasing wherever you see a plus. So from -2 to 0, then from 2 to infinity, the function is increasing. Where is it decreasing? From -infinity to -2, and then from 0 to 2. Okay? The thing is that we're going to find all of this information, and the idea is that we're going to put all of this together to produce a picture later on. Okay? So, but before we do that, we need to talk about another idea, which is this notion of concavity. Because knowing that a function goes down is not enough. Because as I mentioned last time, if a function goes down, it could do it in 2 different ways. It can do it in this shape or in this shape. Which one of the 2 is it? But if it goes up, it could do it this way or this way. Which one is it? So we need to talk about this. The information about this is encoded in the second derivative of the function. The first derivative gives you information about going up or down, okay? And maximum, and therefore maximum minimums. But if you want to know how you go up or how you go down, you need to go to a second derivative, okay? So talk about that. But before, let me do a couple more examples, because I only did one like this. So, do you have questions on what I just summarized? This is what happened on Friday, okay? All right, so let's do a couple more examples. Maybe this guy, so let's start. So find monotony. So the word monotony is just a fancy word for increasing, decreasing, or constant, okay? It's just what's the function, what's the monotony of the function. Whether it's going up, down, or staying the same. So find monotony and relative extreme. let's see, let's start with something easy. I say easy is that, computationally it should not be too bad. So let's start with a cubic, and then let's do a trigonometric one. Let's analyze it on the interval from 0 to 2 pi. And then let's do a rational function. Just because this one could be, interesting computationally speaking, like the algebra, and get interesting. Okay, so let's do this. So solution. So when you want to find whether a function is increasing or decreasing and the relative extrema, you need to look at the first derivative. Okay, so that's the first thing, find the derivative. All right, so we have a cubic here. What's the derivative of this function?
3x squared minus 3.
So that's 3x squared minus 3. Okay, now I want to find the sign of the first derivative, because once we know the sign of the first derivative, we're basically going to know the monotony, and also we're going to be able to see what the relative extrema are. Okay, and to find the sign, you need to find the zeros and the value that makes it undefined. That's exactly what the critical points are for it. Okay, so we need the zeros. What are the zeros of this function? So let's see. When you do this, it's good to have this expression in case you need the second derivative, but factor as much as you can also. So it's good to keep in mind this expression, because if you need the second derivative, this is the good one to keep taking derivative. Okay, but to work with f prime is better if you can factor. So I'm going to work with f prime now, so this is the one that I'm going to be looking at. So we can easily see the zeros. What are the zeros? So -1, 1, and undefined? None. So these are my critical numbers, okay? Remember, the critical numbers are precisely these guys, the ones that make the derivative 0 or undefined. So now we are ready to write down the sign of f prime. It's very important that when you're doing these things, you specify what function we're talking about, because there are many functions here, okay? You have the function f, then we have f prime, later you're going to have f double prime. Those have different formulas. Make sure you don't plug in the wrong place, okay? So here, this is about f prime. Everything I'm going to do is with f prime. I don't care about f right now, okay? Okay, so to find the sign, what you do is number line, then plot the zeros, and the values are make it undefined. In this case, we only have the zeros and the values, and there's no value that makes it undefined. Now the line is split into 3 intervals. Just test the function in each of the intervals, okay? When it's a polynomial, you can use what you know about multiplicity and behavior and all of that. But if the function is not a polynomial, then you just literally pick a point and plug it in, okay? I'm just gonna do that, that way you get used to it. So let's pick a point here. Give me a point in this interval. -2. We plug it in. There is no need to actually evaluate it. The first factor, what is it? Positive or negative?
Positive.
So I will be negative. The first factor.
It's negative.
It's easier to plug in the factor version, because that's easier to see. Okay, so that's a negative. And then the second factor, what is it?
Positive.
Negative. -2 minus 1, that's a negative. Yes? So negative times negative is a positive. Do you understand what I'm doing? I am working with this one now. Okay? So I'm thinking about -2. So just any number that you want in this interval. Just thinking about -2. And then when you put it here, the first one is a negative, the second one is a negative. Yes? Negative times negative is a positive. So the value here will be positive. So that's why I put a plus in there. Go to the next one and repeat. Give me a number in that middle interval.
0.
0. So what are the signs for each of the factors? Positive. And then the second one is a negative. So positive times negative?
Negative.
Negative. Do you understand what I'm doing? Go to the next one and repeat. Give me a number in the next interval. 2. Plug it in. What do we get? Positive times positive. So that's a positive. Now, what does this mean about the function itself? So remember, this is the sign of the derivative. So this means the derivative is positive over here, it's negative over here, and it's positive over here. Okay? So what does this tell you about f? So now I'm gonna draw some arrows telling me the monotony. So what happens from negative infinity to negative 1? Is the graph going up or down?
Up.
Function is increasing. Remember, positive derivative, function is increasing. How about in the next one?
Down.
It's going down. And then
Up.
up. Okay, so here in this picture we have the monotony already. Okay, now let's find the relative extrema. So we have two candidates, which are the critical numbers. In this case, negative 1, 1, those are my candidates. Now let's classify them. What can you say about negative 1?
Maximum.
That's a relative maximum. Does everybody understand how to see that? Just literally, do it with your fingers, and then you're gonna be able to see it. Relative maximum. And how about this guy? That's a relative minimum. Now, of course, that's the location, right? You want to actually see what the value is, you have to plug it into the original function, okay? If you want to see the white value. This is just the location at which they are happening, okay? So, conclusion is the monotony of the function is increasing from negative infinity to negative 1, and also from 1 to infinity. I don't like to write the union here. In the homework, they may require you to put union when you have multiple intervals. Technically, doesn't really satisfy the condition of increasing, because you could have this overlapping. You could have something like this, for example. And then even this function is always increasing because it's always going up. But you see, for example, it's not differentiable at that point. And then if you put a union, increasing means that as you go from left to right, you need to move from bottom to top. Okay? For example, if I pick this x, this is the reason why I don't like to put that. Remind that we are here. If you pick this x, whatever this is, and then pick this other x. No, sorry. No, I'm gonna say, and that one, but this one. This is my x2. Here, the definition of increasing is not satisfied because x1 is less than x2, but f of x1 is actually higher than f of x2. And increasing is supposed to say that if the input is smaller, then the output has to be smaller. That's what increasing is supposed to do. Okay? That makes sense if you have a continuous function. But if this function is not continuous, which then you have to split into two intervals, okay? Then that increasing condition doesn't really work. That's why I like to do unit. But anyways, if the homework requires you, then just put the U and that's it. Now in the exam, if you put the U, that's okay. I'm not gonna penalize you. But I want you to understand that really how much better in this situation. All right, that's increasing and then decreasing. What is decreasing? Negative 1 to 1. Now I also don't like to include the endpoints because closed intervals here doesn't really make sense because at a point itself, the function is neither increasing nor decreasing. Okay, so this is just inside an interval. Again, if you are 100% sure that you're doing it correctly, the homework is not taking it, then try putting a closed interval. It's not technically wrong, but there is no reason why you need to put a closed interval because endpoints are not really important. What we care about is the interval itself. At a point itself, the function is neither increasing nor decreasing. You cannot talk about that at a point. You need an interval. Okay, so that's that, and then relative extrema. So we found a relative max. Where? Negative 1. And we found a relative mean. Where?
1.
Relative minimum at 1. So I will just say this, but remember, when we are graphing, you need to know everything. You need to know also the y value. How do you find the y value?
Plug it into the function,
the original one. Remember, you're going to have multiple formulas. You're going to have f prime, f dot prime, a bunch of stuff going on. When you actually want to know what the point is, x comma y, you always have to pick your x's, but then you need to plug them into the original one, okay, to get the actual one. All right. Questions for this one? Did you understand this? So the idea is exactly the same. What could change is that, if the function is more complicated than just a polynomial, then this process of finding finding the zeros and so on could be a little bit more complicated, okay? May require more knowledge. Like in the next one, we need to do a little bit of trigonometry, okay? Because the function is a trigonometric function. But the idea is the same. Once you find your zeros and undefined, and you are here, it's the same. Pick point from E and determine the sign, okay? All right, so let's see, let's do f of x equals 1/2 x minus sine, and we're just interested from 0 to 2 pi. All right, derivative. What is it? What's the derivative? 1/2 minus cosine of x, right? So it's 1/2 minus cosine, and now we need to determine the sign of this function. Now remember, we need to find the zeros, right? So zeros, we need to solve 1/2 minus cosine equals to 0. That means cosine of x is equal to 1/2. So how many solutions are we going to get from here?
1,
2 solutions. Whenever cosine is positive. Where is cosine positive? Quadrant 1 and 4. So we're going to get 2 solutions. One coming from quadrant 1, another one coming from quadrant 4. Yes? So what's the quadrant 1 solution? So you need to ask yourself, what angle do you know whose cosine is 1/2, and that's 60 degrees, or pi over 3, right? So that's pi over 3. And remember, the quadrant 1 solution is a reference angle, so then you can use the reduction formula to find the other one. So in quadrant 4, what's the reduction formula for quadrant 4? 2 pi minus the angle. If you don't remember, just draw the picture. Do you know what a reference angle is? So when you draw your angle, you draw it here in quadrant 2. This is an angle in quadrant 2, right? The reference angle is the angle. So this is theta. This is the angle theta. Now the reference angle is always acute. It's always less than 90, and it's the angle made by the terminal side of your angle and the x-axis all the time. So in this picture, the reference angle is this guy over here. It's the angle, the acute angle between the terminal side and the x-axis. It's not this one. This is the y-axis. Okay. So for example, if it's in quadrant 4, if you have an angle in quadrant 4, like in our case, if you have an angle in quadrant 4, something like this, so this is your theta. The reference angle is this one over here. Do you understand this? So now, for example, let's look at the picture here in quadrant 2. What would be the reduction formula? What do we mean by reduction formula? How are alpha and theta related? How is the angle and the reference angle related? Just look at the picture. In the quadrant 2 case, for example, what relationship can you say between alpha and theta? Just look at the picture. What can you say between alpha and theta? If you add them, you get pi, right? Put them together and you get pi. So what you can get from here is that alpha plus theta is pi. And the idea is that typically you know theta, typically you know alpha and you want to know what theta is. So this tells you then that theta is pi minus alpha. That's your reduction formula for quadrant 2. Okay? Similarly, in quadrant 4, you draw your picture, look at it. What relationship can you say between alpha and theta? Equals 2 pi. So if you do alpha plus theta, you get 2 pi. So what's theta? 2 pi minus the angle. Okay? And then you can do the same thing for quadrant 3 to get the reduction formula for quadrant 3. Just that when you use this many times, then you just remember the formula. Or think about the picture in your mind really quick. Okay? Anyways, here the reference angle is always a quadrant 1 angle, the quadrant 1 solution. So in this case, it's pi over 3. So the corresponding one to quadrant 4 is 2 pi minus pi over 3. Because that's our reduction formula. And what is this? 5 pi over 3. Questions? Okay, so we found these are the zeros. Are there any values that make it undefined? No? So that's it. So we are ready to write down the sign. So let me say f prime undefined, none. So we write the sign. Okay. So remember, we're only interested from 0 to 2 pi, so we're working inside this interval. And then we found pi over 3 and 5 pi over 3. And let me put the formula for f prime here in view. Is that one over there? So now, the same thing. Just pick points in each of these intervals and plug in. Okay. For example, you can either do that or do something that I explained in the notes here. You can play with the graph. I'll show you how to see that quickly. But let's do it the way that we have been doing all the other points. So you see, once you get to this point, then it should be straightforward. Just make sure that you pick a point that is in here. You don't pick something that's somewhere else. Remember, pi over 3 is, what angle is this? 60. So what point should you pick in here? You can pick pi over 6, which is 30, or maybe pi over 4, which is 45. Pick easy stuff that you know how to plug in. So for example, let's pick pi over 6. If we put pi over 6, what do we get? What's cosine of pi over 6? That's square root of 3 over 2. So that is the square root of 3 over 2, whatever that is. And then we need to do 1/2 minus that. So that would be 1 minus square root of 3 over 2, but 1 minus square root of 3 is negative. So that's a negative. Again, just put in your calculator and you plug it in. Okay? So this would be a negative, because 1 is less than the square root of 3. Then let's pick one here. Pick a point from the next interval. 5. Okay. We put pi. What do we get? What's cosine of pi? -1. Why everybody's quiet? You should be screaming -1. Cosine of pi is -1. You can also pick pi over 2, by the way, and it's easier because then you get 0 for cosine. But that's fine. We pick pi as -1. There's a minus in front, makes it positive, right? So 1/2 plus 1. So that's a positive. And let's pick something here. Give me an angle in here. Let's see. Translate this into degrees to make it easier. What is this in degrees? That's 300. Does everybody see that? Pi over 3 is 60. 60 times 5 is 300. This is 300. Just pick something that's bigger than 300 and less than 360. So you can pick 330. That will work. Or what is it? 330, which is the one coming from 30 degrees in 12 and 4, which is 11 pi over 6. You understand this? Okay. So, but actually, you can even do it easier. No matter what value you pick in here, now let's do it another way. No matter what value you pick in here, no, actually no, because cosine is positive, and then we don't know. It's 1/2 minus that. Anyway, so we pick 11 pi over 6, corresponding to 30, and then it's going to be the same situation that we had in here, right? If we pick 30 here, the same thing that we did with 30 is going to happen with pi over 6, it's going to happen with 11 pi over 6. So it's going to be negative. Just put in your calculator, okay? It's going to be negative. And then that's it. So decreasing, increasing, decreasing, okay? So what's this point?
Minimum.
So that's a relative mean. What's this point?
Maximum.
That's a relative max. Okay, I'm not going to write all of this. I'm just gonna keep the picture. Hopefully you understand that with this picture, we have everything we need for this question. Yes? All right, let's see who can tell me in words. What is this function increasing?
Pi over 3 to 5 pi over 3.
Good. What is it decreasing? 0 to pi over 3 and
5 pi over 3.
5 pi over 3 to 2 pi. Do you understand this? The arrows are telling you that. Now let me just show you. In this case, this sign could have been done as follows. If you want to know how one, basically, to figure out this is the derivative, right? figure out when this is positive or negative is equivalent to ask how do these two functions compare, right? If you think about these guys as functions, 1/2 is a function, cosine is a function. So, for example, whenever cosine is above the graph of 1/2, what's going to happen to this sign? Will this be positive or negative? It will be negative because cosine is bigger. They're doing 1/2 minus something bigger. You understand this? So if we graph these two functions, whenever cosine is above, this is going to be negative. Whenever cosine is below, this is going to be positive. And whenever cosine meets this function, then we're going to get 0. Yes? We know when the meeting happens. The meeting happens at pi over 3 and 5 pi over 3. We found that. And we also know how to graph these functions. So, graph them. So let's see. Here is 1. Here is -1. That's 2 pi. And as you know, cosine starts up here, down here, middle, and then up. So this is the graph of cosine. It's pi over 2. That's pi. This one is 3 pi over 2. And then 1/2, we have it right here. That's 1/2. Yes? And these points that they are meeting, can you tell me what they are? What are those blue points? What's the x value? Oh, we found them. Pi over 3 and 5 pi over 3, right? That's when the derivative is 0, meaning that the two functions are equal. So this is a pi over 3, and this one here is our 5 pi over 3. Now you can see, from 0 to pi over 3, cosine is above, so this is a negative. Right? You see it right there. Then between pi over 3 and 5 pi over 3, so from this blue point to this one, cosine is below. So what can you say about this? It's going to be positive because this is a smaller value. Yes? And then from 5 pi over 3, from this blue point, 2 pi, the cosine is again above. Then this is going to return to negative again. So in this case, we can do that, and this is actually faster and easier than picking points and plugging in. Okay? Because what if you pick the wrong point? Or what if you plug in wrong? Make sure that if you're using a calculator, you have it in radian mode, right? And all of that business. If you're going to use a calculator for this. Okay. Questions? And then let's do this one. X to the 4 plus 1 over x squared. Okay, so we want to find the derivative. Here we have two choices. We either use quotient rule, or what can we do here? We can split it. We can split it. Good. So let's do that because it's easier to find the derivative if we split it. So how do we split this? What is this equal to? 2x. That will be x squared plus 1 over x squared. Yes? Just writing this as two fractions. Does everybody see this? And then the second one, we can write it as x squared plus x to the -2. So this is easier to find derivative because now we just need to do power rule. Okay? All right, so let's find f prime. So f prime is 2x minus 2x to the -3. So that's 2x minus 2 over x cubed. Remember, of course, the price that you pay is, yes, it was easy to find derivative, but now we need to combine. Okay? So we avoid the quotient rule, but then the quotient rule already gives you the answer as a fraction. Here, we need to combine to be able to get the fraction. Okay? But remember, we need to find zeros, undefined. Undefined you can see here, but the zeros, then you have to solve. So it's easy to just combine to get a rational function. Are you comfortable combining this, or do I need to explain this little by little? Let's see, who can tell me what needs to be done here to combine these two guys?
Multiply the top and the bottom by x cubed.
Of what? Of the first one, right? So remember, you just need to have the same denominators because there is a 1 here, I just want an x cubed in here. So multiply top and bottom by x cubed. So you're going to have a 2x to the 4 up here. So that's 2x to the 4 minus 2 over x cubed. Are we good? And now factor. Now, why is it helpful to have this expression? Because then, if you wanted to do something else with this function, like find concavity, graph, or whatever, you will need to find the second derivative. And this one right here is very comfortable to keep on taking derivative. Okay? Otherwise, if you would leave it like this, quotient rule. Then you have something like this, quotient rule again. Okay? So you have to do multiple quotient rules, while like this, it's pretty easy and fast. Okay, so let me just keep working here a little bit. So I'm gonna factor out 2. Have a difference of squares on top. So that would be x squared plus 1, x squared minus 1. And then you can keep going. And this is x plus 1, x minus 1. Remember, this is f prime. So now we can easily read off the zeros and the values and make it undefined. Now we are going to analyze the sign. What are the zeros? A fraction is 0 whenever the top is 0. So what are the zeros? Negative 1 and 1. Yes? Remember, a function is, if you have a fraction, the only way that a fraction can be 0 is if the top is 0. That's it. Okay, that's why a factor, so we can easily see the zeros. This factor x squared plus 1 it's always positive. It's not going to bring any 0 there. And any value that makes it undefined, x equals 0. Now, x equals 0 is not really a critical number. Why? X equals 0 is not a critical number because it's not on the graph. To be a critical number, it has to be a point on the graph. The function, the original function is not defined as 0. Do you see that? So this guy is not a critical number. However, for sign purposes, you need to consider it. Because, you know, this, what happens is that this is a vertical asymptote, as you know, because that's a rational function. As a vertical asymptote at 0, the y-axis, and you know, the function may be doing something like this, say, for example. So, you see, it changes sign around 0. To the left is positive and to the right is negative. So if you don't consider 0 in your sign analysis, you're going to miss it. Okay, you're going to miss this thing. Now, understand that if you are looking for relative extrema, which we are, even if you see a change in sign, if you see a change in sign around 0, you need to skip it and not consider it because that's not a point on the graph. X equals 0 is not in the domain. Do you understand this? But we need the sign of the derivative to determine monotony, so we need to consider that. Let me just say that here the critical numbers are only these guys. Okay? 0 is not a critical number because it's not on the function, so I would say not in the domain. But nevertheless, it will be considered for the sign of the derivative. So sign of the derivative, line, put the values and make it 0, the values and make it undefined. Okay, so we have this. Now the real line is split into 4 intervals, big points, plug it. Okay. All right. Give me a point in the first interval. Negative 2. So let's see. The factor x squared plus 1 is always positive, so we don't have to worry about that. Okay. Let's just the sign of that expression is determined by whatever happened with the 3 factor x plus 1 is minus 1 and the x cubed. You see that? Because the other stuff is always positive anyway, so I'm not going to worry about that. So negative 2, plug it in. So focus your attention in here. This is what you should focus your attention on, okay? Because the rest is just positive all the time. Okay, negative 2, first factor, what is it? Positive or negative? Negative. Second factor? Negative. The bottom? Negative. What's the overall sign of something like this? Negative. Does everybody understand this? Negative and negative is positive. Positive divided by negative is a negative. Yes? Go to the next one and repeat. So, pick a point in between. Negative a half. Okay. The first one, positive or negative? First factor. Positive. Negative a half plus 1 is positive. negative 0.5, right? So that's a positive. The next one, negative. The bottom, negative. So what's the overall sign here? Positive, because you have negative divided by negative. So that's a plus. Do you understand this? Another one? The next one?
1/2.
1/2. So what are the signs? Positive and negative. 1/2 minus 1 is negative. And then positive. What's the sign?
Negative.
Negative. Last one. Pick a point. Okay. What are the signs? Positive, positive, positive. So a positive. Okay. So here we have the sign of the derivative. Now we make our conclusions. Let's see. Tell me where it should go up or down with the arrows. What do I do?
Down.
Up,
Down.
up. Okay. So by looking at this picture, does anybody understand the monotony of this function when it's going up or down? Okay. And then now let's classify. What's happening at this guy? At -1,
Relative negative.
we have a relative minimum. What happens at 0?
That doesn't stop.
We don't count it.
Nothing. Okay. Not on the graph. Even though we see a monotony changing, you see around 0, the function is going up and then it's going down. And it looks like what's happening is something similar to what I showed you. Here it's going up, here it's going down. Right? So to the left is going up, to the right is going down, but there is no maximum. Why? Well, because there's not a point in the graph to begin with. Okay? Okay, so nothing happens there. And then what can we say about x equal 1? Use your fingers.
Relative minimum.
Use your fingers. Follow the arrows. Let's see, I want to see your hand. No, around 1.
It's going down.
But don't stop.
It goes back up. That's why I'm like.
So use your finger. So what do you have in there? A minimum. I'm trying to tell you it's very easy. What you have this picture is very easy. Can you see this in your mind? Well, the one in the middle is weird because remember, it's not really a point, but once it is a point on the function, this one you should have this picture in your mind, and here you should have this picture in your mind, this sort of behavior. Do you understand this? Use your... Okay, so relative minimum. So this time we have two relative minimum, there is no relative maximum, and we have the monotony right there. Okay? Okay.
I have a question.
Yes.
So when we write where it's increasing and decreasing, what do we do about the 0 point? Do we just not even look at it?
Increasing from -1 to 0. Remember, open parentheses. That's why I open parentheses all the time. Point itself is not really relevant. What we actually have is a vertical asymptote at that point. Are you okay? All right. Remember, we are putting this information together to produce pictures, so you need to understand what this is telling you. Okay? All right. So, okay. So that was that. So that was first derivative test. So now, as I mentioned, there is this question about concavity. Now we know when the function goes up, we know when the function goes down, but the question is how does this happen? Okay, how is it going up? How is it going down? What's the shape? And that's the notion of concavity. So let us analyze this. So let y equal f of x be a function. And say that we know that the derivative of the function is positive on an interval I. So what does that mean about the graph of the function on this interval? What does this mean about the function f on the interval? It's increasing. The graph is going up, right? So then we could have the following. So over the interval I, our function f could look like this. This could be f, but it could also look like this. Do you understand this? So imagine that this is your interval I. This is happening over the interval I. So far, with this information that I'm giving you, all you know is that the graph of the function is going up. So it could be going up with this shape or with a shape like this, or maybe with a line. Okay. Okay. So I don't know. It could be going up like this as well. And these are the only three possibilities that could be happening at this point. Do you understand this? You get this information from the fact that I'm telling you the derivative is positive. That means that the function itself over this interval has to have one of these three pictures. So we want to somehow be able to tell, which one of these pictures is it, okay, over this interval. Which one of these three shapes is it? Okay, so the thing is that the derivative itself is not going to tell us anything. So let's try to see if we can figure out something else that's going to help us. And the idea is the following. For example, what's special about this shape? Okay, what's special about this shape? And here is something that geometrically is nice, but if you want to work with it, it's actually pretty difficult. But something that you can say is that this shape always has the property that at any tangent line that you draw, the function is always on top of it. So you see, if I pick any point in there, and then if you draw the tangent line at that point, the function is always above the tangent line. Do you see that? Just look at the picture. And even if your shape was like that, still that same property holds. You see? The function is always on top of the tangent line. A shape like that is called concave up. Okay? And the reason why it's up is, well, the reason why this name is chosen, you can think of it because the function is on top of the tangent line. Okay? Now, using the same idea, what can we say on the other side? If you pick any point and you consider the tangent line, what happens?
It's below.
You see, the function is always, the graph of the function is always under or below the tangent line. Okay? So, because of this, we call this concave down. Because, the graph of the function is under the tangent line. And then the other one, well, the other one is that the function is actually the tangent line. If you pick any point you want,
It goes straight on the line.
then the function is the tangent line itself at that point. Okay? Now, you can imagine, we want to be able to detect this from the formula. If I give you an equation, how do you know whether the graph of the function is on top or below any possible tangent line on a given interval? Geometrically, this is a nice and easy thing to define, but algebraically, to work with this and determine concavity is not really a good idea. So we need a better definition. Or we can take this as a definition, the geometric one. So let's try to see if we can characterize this. Can we do something to the function to detect this concavity? Okay? And this is what I want to emphasize. This is just to motivate the names, because then you can tell me, why do they call it concave up and not something else? Well, because it's coming from this geometric fact that the function is on top of the tangent line, and the other shape is coming from the fact that the function is below the tangent lines all the time. Okay, now how can we characterize this? And let's see. I draw slopes here. You should be looking at the tangent lines. How can you say that the tangent lines are below the graph all the time? Well, let's move from left to right. What do you notice that's happening to the slope of these tangent lines as you go from left to right? Look at the picture. Does everybody see that the slopes are getting bigger and bigger? The lines are getting more steeper. Yes? Even if the shape was like this, that's also true. Because you see what's happening here to the left. What sort of slope do we have? This is a very negative slope. And then what's happening? As we go from left to right, what are those negative numbers doing? Getting closer and closer to zero, right? We hit 0, and then
We go
they
up.
start to become more and more positive, the slopes, right? So we can say that on this interval, what's happening is that the slope is increasing. So concave up, a characterization is, okay, we can say the slope is increasing. Do you understand this?
So concave down.
And we know, so now we're going to go there, but we know how to characterize this algebraically now. Okay? What gives you information about the slope? The derivative. And what tells you, now derivative is a function. What does it mean to be increasing? Positive what? Derivative. So the function in question here is a derivative, and we want to say it's increasing, so that means its derivative, so the derivative of the derivative must be positive. In other words, if you want to get to the concavity, you need to look at the derivative of the derivative and require it to be positive, right? Here we are saying, I wrote it like this so you can see, here we are saying that this function, which happens to be the derivative, but here we are saying that this function is increasing. Does everyone understand this? Because the derivative of it is positive. Now, as you know, this is just second derivative. And this is a better definition for concavity for us because you can figure this out from the formula. You have a function, look at the second derivative, whenever it's positive, you know, on that interval the function will be concave up. Do you understand this? Now, let's use a similar idea on the concave down case. So, for the concave down, once again, geometrically means the graph of the function is always under the tangent line, so you know how the shape is. But how do we detect this? So let's see. Let's focus on the slope again. What can we see about the slope? What happened to the slopes of these functions? They start from very positive, right? But as you start moving from left to right, notice that the lines are getting more and more and more horizontal, right? And then if it happens to be the full curve, then they start to become more and more negative. Yes? So the numbers, the slopes are getting smaller and smaller. So concave down means slope is decreasing. Do you understand this?
Yes.
And how can we characterize this now? That means that the derivative of the derivative is negative, right? Because the function is decreasing when its derivative is negative. In other words, the second derivative is negative. So that's what we're going to take as our definition. If you want to see when a function is concave down, find the second derivative and figure out when it's negative. Okay? And then, you know, the other case is easy to see because, I mean, you can easily spot the other case. We don't even need to go to the second derivative. This just means that the slope is constant, right? Slope is constant. And then, how can you see that? Well, when you take the derivative, you get a constant, right? So there is no reason to go to a second derivative to see that case. Okay? Saying that because, or you could say, well, that's equivalent to say the second derivative is 0. Okay? Over the entire interval. You could write that down. So, this is how we're going to determine concavity of a function. The function is going to be concave up whenever the second derivative is positive. Function is going to be concave down whenever the second derivative is negative. So again, it's a matter of finding the sign of the second derivative. That's why you need to know how to find sign of functions, when it's positive, when it's negative. Okay? So we're going to play the same game that we did for the first derivative, but instead of getting information about increasing or decreasing, we're getting information about concavity, the shape of the graph. Okay? Is this clear? All right, so let me write the definition, which is what we just did here. So definition. Let y equal f of x. Now for this, of course, we need the function to be twice differentiable at least. You have to be able to take the derivative twice. Okay. Be a twice differentiable function. On an interval I. That means that inside this interval, the second derivative exists at every single point. You know, the first derivative exists and the second derivative also exists. So be a twice differentiable function on an interval I, then f, the graph of f is concave up if and only if, what's the condition? The second derivative is positive, and then remember the shape that we're talking about here is this type of shape, okay? That's what concave up is. And then the other condition is, the other definition would be that the graph of f is concave down. Okay, let me say concave up on I, because you know, concave up on I if and only if second derivative is positive. And the graph is concave down on I if and only if, what's the condition?
The second derivative is negative.
The second derivative is negative. And this is the shape, okay? And in fact, if later on you forget this condition, hopefully you're not gonna forget the shapes, okay? And then you can recover this pretty easily. Hopefully you will remember that you need to look at the second derivative, and then probably you may be confused. Okay, I don't remember. Is the positive concave up or down? Which one is it? Which one is the positive? Which one is the negative? Then it's very easy to figure that out. That will be our first two examples. What's the function that comes to your mind when you see this shape? X squared. What's the second derivative?
2.
2. Is it positive or negative?
Positive.
Positive. So this is how you can associate second derivative positive means this shape, concave up. Okay? What formula comes to your mind when you see this shape? Negative x squared. What's the second derivative? Negative 2. It's negative. So this shape, which is concave down, is associated to negative second derivative. So I also use that trick because you know, sometimes you may not really, then just think about this. You know the shape, okay? You know the shape, what concave up is concave down, and then just x squared and negative x squared is going to remind you of this statement, okay? Do you understand this? Okay, so let me actually write those. So example, for example, the function f of x equals x squared, then f prime is 2x, f double prime is equal to 2. So this is positive on negative infinity, positive infinity. So f is concave up on this entire domain. And we know that, right? It's a concave up function. And then similarly, if you look at negative x squared, then its derivative is negative 2x. Second derivative is negative 2, which is less than 0 on the time real line. So f is concave down. You okay with this? All right. So let me bring this guy down a little bit. Let's do a third example, and that's gonna introduce this next notion about x cubed. F of x equals x cubed. If we want to know the concavity of this function, what do we need to do? What do we need to look at?
Second derivative.
The second derivative. So what's f prime?
3x squared.
3x squared. What's f double prime?
6x.
That's 6x. So now for concavity, we need to look at the sign of the second derivative, right? So sign of f double prime. Remember, we need the zeros. What are the zeros? X equal to 0. Undefined? None. So that means that as far as the second derivative is concerned, Only 0 is an important point when it comes to the sign of the second derivative. And then, we repeat what we have been doing. So this is the formula you need to pay your attention to. This guy. This is your focus now. So to the left of 0, is this positive or negative?
Negative.
So that's negative. To the right of 0?
Positive.
Positive. So what can we say about the function from negative infinity to 0?
Okay, down.
We're talking about concavity, not relative extrema. This is, be careful, this is second derivative. It's not going up or down, okay? This is about shapes. So the function is like this here. So if you want, just write CD, not for compact this, but for concave down, okay? And then from 0 to infinity, what is it?
Okay.
Concave up. Remember, this is telling me that second derivative is negative. This one is telling me that second derivative is positive. You okay with this? So it could be that a function goes from, changes concavity. For example, here, this is the cubic, right? So let me draw it here. How does the cubic look like? It's like this, right? And then what can you tell me about this first interval? What's the concavity here? That's concave down. Then comes this special point 0, and then it does this. What's this concavity? Up. This point is special. This is the point at which the function changes concavity. We call this an inflection point. Okay? Which is the next definition that I'm about to write. So the point is called an inflection point if the function changes concavity around this point. In other words, if the sign of the second derivative changes around the point. From negative to positive or from positive to negative. Okay? So that's called an inflection point. Do you understand this? All right. So remember, monotony and relative extrema, where is this found? Where is this information found? First derivative. Concavity and inflection points? Second derivative. Okay? And you need all of these to produce a picture. Okay? Because it's not enough to know when the function is going up or down. You need to know how is it going up, and if it's going to change how it goes up. Like in this case, it's always going up. But it changes the way it's doing it. It's doing a concave down way, and then it changes to concave up. That moment in which it changes has a name, inflection point. Okay? And to find it, that's exactly when the sign of the second derivative changes. Okay? So for example, this here would tell me then that this guy is an inflection point. Okay? Because it changes concavity. All right, so let me write that definition, and then we do examples. All right, so if f is a continuous function on an open interval I containing a value x0, okay, let me write a value c. A value c, and if f changes the direction of its concavity, do you know what I mean by this? When I say it changes the direction of its concavity? Well, that means from concave down to concave up, or concave up to concave down, okay? If it changes concavity at the point c, f of c, this is happening on the graph, so at this location, this is the x and this is the y, okay? Then we say that f has an inflection point at c, and we call the actual point c, f of c, the x, y, on the graph of f, an inflection point. So if I ask you to find the inflection points, you have to give me the x and the y. Now, if we're in a rush, we just, usually we give the location and that's it. We have an inflection point at this place. But if you want to know what the point is, you need to plug in and get the y. Where do you plug in? On the original function. Okay? On the original function to get the y. Are we okay with this idea? All right, so then let's do some examples. Let's find concavity and inflection points and all that. Let's see. I don't want to do too many just because I need time to do more stuff. So let me pick and choose from here. Okay, so example. Determine the intervals where the function is concave up and concave down. Okay, then also find all inflection points. Now it goes without saying because of this, right? This is a point on the graph because you're flowing in, so this has to be a point in the domain and all of that business. Okay, because you're flowing in. Okay, there's something that's missing in this definition that's important, and it's the fact that this point has to be a stationary point. In other words, remember, we're going down to a second derivative. So when I mean, it's implying what I just said, because in this definition, this is a subtle thing. You have a twice differentiable function. So if you're going to have an inflection point, it's going to happen inside this interval, because that's what inside an interval in which it changes concavity. So the function has to be differentiable at that point. In other words, the derivative must exist. If you think about an absolute value function, right, there's no change in concavity at 0, because there is actually no concavity around 0, right, because you have a linear shape all the time. But what happens at 0? At 0, the derivative is not defined. So you cannot even talk about the second derivative at 0. Do you understand what I'm saying? Yeah. So if you get to the second derivative to analyze concavity and inflection points, that point that you're analyzing, it has to be a stationary point, meaning the derivative must be 0. Okay? The reason for that, because inflection points on the graph are relative extrema of the derivative. Okay? So remember, the derivative itself is a function. So if you're going to have an inflection point on your graph, then that inflection point of the original function is going to be a relative extrema on the graph of the derivative. So for example, think about this one, x cubed. 0 is an inflection point, but the derivative of x cubed is a parabola. And at 0, what we have is a relative minimum, right? We have a relative extrema. So relative extrema of the derivative, they are the candidates for the inflection points of the original function. Okay? All right. So what I want to say here is I should throw in somewhere that f prime of c must be defined. So if it has a continuous function of interval I containing c, and you change the direction of its concavity at this point, and f prime of c exists. In other words, you can talk about slope, okay, at this point for the function. That's what I want to say. You can talk about slope. That's what this line, little line means. Then we have an inflection point, etc., etc. Okay, so determine intervals where the function is concave up and concave down. Find all inflection points. Okay, I'm going to abbreviate inflection points by something like this. I could write IP, but IP may stand for too many things. So this is probably something like this for inflection points. Okay. All right. So let's see. You pick and choose from here. So let's get an interesting one. Let it go. Let's take a look at this one. Then let's look at a rational one. And let's do one that we cannot avoid quotient rule, so we don't forget that. And then, okay, so let's do a trigonometric example also. It's just doing several, every example here has something, a little thing, so I need to do one more. So we do a product rule. Yeah. Okay, so let's do this. And the whole point of me doing these examples is because of the algebra involved, okay? And since I know that sometimes algebra is not really your strongest friend, then, I want to make sure that you see different situations and how to handle them. Because, the calculus content itself is not really that complicated. Just find second derivative, and then the rest is pre-calculus. Analyze the sign, the zeros, and all of that business, okay? The calculus is just find the second derivative. All right, so let's see. I'm going to do number 1, then I'm going to let you do number 2 while I take attendance. So the solution, let's do number 1 so you see what it takes. So this is about concavity and inflection point, so we need to go directly all the way to second derivative. Now, whenever you're analyzing a function, it's always good to keep in mind the domain. What's the domain of this function? What's the domain? Or real number. There is no issue here. You can plug in whatever you want. Okay? Remember, this is really 1 over e to the x squared over 2, but this is never 0. Exponentials are always possible. Okay? So you can plug in whatever you want. So there is really no initial concern for us. So let's just go straight to the derivative. Okay, f prime. What do we need to do? Chain rule. So that's e to the negative x squared over 2 times the derivative of this. And what's the derivative of this? Which is negative x, right? So let me write it down. The 2's cancel out, so we get negative x times e to the negative x squared over 2. Everybody okay with this? Remember, chain rule. Now we need to go down to the second derivative. What do we need to do to find the second derivative? What technique? Product rule. There is a product right there, so we need to use product rule. By the way, let's understand that we already know what's the derivative of this second part. What's the derivative of this second part?
That whole
This.
thing.
All of that, okay? So that's gonna come up in the formula. There is no reason to rewrite all of these again. We just write down the simplified result, okay? So, product rule. Derivative of the first, negative 1 times the second, plus the first, times derivative of the second. Now, the derivative of the second term, we already know what it is. It's this. So we just write it in there. Do you understand? Okay. So we took the second derivative. Now we just need to do the cleanup process and then work with this. So let's do it. So we're gonna have actually x squared e to a negative x squared over 2 minus e to a negative x squared over 2. I flip it because this one became positive and this one is negative. Now, because I know I need to find zeros and all of that, then you need to factor this. It should be clear what to do here, right? So we see that there is a common factor between those two terms. So let's factor that. What's left in the parentheses? X squared minus 1. And then there's a difference of squares. So we get our second derivative. And I mean, in this case, this doesn't really matter because this is never going to be 0 anyways. But it's a good practice not to keep negative exponents. So I'm going to bring this guy down. So that becomes x plus 1, x minus 1 in the top, and then this guy in the bottom. Are you okay with this? I just brought this down because it's a negative here. Okay? But now we want to analyze the sign, right? So sign of f double prime at this point is exactly the same thing as what we were doing before. We need to find zeros and values that makes it undefined. So what are the zeros? Negative 1, 1. And undefined? Undefined? None. This is a fraction, it will be undefined if the bottom is 0, but this bottom is never 0. Exponentials are always positive. Do you understand this? E to whatever is always a positive number. Okay, so number 9, here is -1, here is +1. So the interval is split into 3 pieces. Just pick points and plug in. Remember, the denominator here is always positive, so we don't have to worry about that. The sign of this is determined by the sign of the top. If the top is positive, the second derivative will be positive. If the top is negative, the second derivative will be negative. Does that make sense? Because you're dividing by something positive all the time. So let's just focus on the top. Pick a number. -2. So what are the sign of the factors? Negative times negative. So what's the sign? Positive. Go to the next one and repeat. You pick a 0, that's a positive times a negative, so that's a negative. Then you pick 2, that's positive times positive, so that's a positive. Now you need to understand that we are analyzing the second derivative. So what are we looking for? Concavity. Don't get confused here, don't start drawing arrows. This is not the first derivative. Yes, this is not the first derivative. So what can we say about the interval from 0 to -1? Concave up. What can we say about the interval from -1 to 1? Concave down. And then from 1 to infinity? Concave up. Now it's time to, so we know the concavity now. Now it's time to figure out inflection points. We do see that there is concavity changing around each of these points. Yes? Here it's going from up to down, and then here from down to up. Now to qualify them as inflection points, we need to make sure that the slope exists. So that the derivative is undefined. So just quickly take a look at the formula for the first derivative. It's this one right here. And if you plug in 1 or -1 in this formula, you will get a number. Yes? So that means we can talk about slope there. So both of those guys qualify. So what can we say about these two numbers?
Inflection points.
So we have inflection points at these two places. If you want to know the actual points, remember you have to plug in. Let's see, this is easy to plug in, so let's plug it in. So since, okay, this is the only example that I'm going to write the full thing. After this, I will just show you the pictures. Okay? So concave up. What is it? What are the intervals of concave up? To -1, and then 1 to infinity. Here the same thing. The homework may require you to write a union and all that. Okay? And concave down. Where is it? -1 to 1, and then inflection points. So it's gonna be -1 comma f of -1. That is, so I put a -1 here, I'm gonna get e to a -1/2, right? So as e to a -1/2. And if I put +1, I get the same thing, right? Because of the square. So e to a -1/2. You can rationalize this, and you can get fancy there. I'm just gonna keep it like that. And then 1 comma f of 1. Okay? So the y location, the y value is the same, but the locations are different. There are two inflection points. Those are the actual points. Okay. Questions? All right. So now give it a try with the other one. So the other one was a rational function. Have fun doing question rule. Let me take a 10.
We're supposed to find the concave.
No, this is about concavity. We're practicing concavity.
Okay.
So find concavity and inflection points.
Okay. Thank you.
That's a 4 down there. It looks weird.
Follows 9.
That's why I'm saying it's a 4. Before you complain. X squared minus 4. Okay, let's do this together. What do we need to do? Why? Because our goal is to go to the second derivative. So we need to find the first derivative, and then we need to take derivative again. Yes? But now, to find the first derivative, one step at a time. First derivative, quotient rule. So let's do it. Everybody remember quotient rule? All right, derivative of the top is 2x times the bottom minus the top times derivative of the bottom. Derivative of the bottom, 2x divided by bottom squared. You okay? All right, so now we play with these and simplify before we go further, okay? Here you can do with 1, like distribute, combine like terms, or you can factor stuff. I mean, you could distribute and then see that the 2x cubed will cancel out. I will actually do it differently. I will factor out 2x. Because, you know, I see 2x in here, so why not? So I factor that out, and then I'm going to have x squared minus 4, and minus x squared plus 1, so that becomes minus x squared minus 1. Yes? Okay, and then these guys cancel, so we get minus 4 minus 5 minus 1, that's a negative 5, times 2, that's a negative 10. So this is negative 10x, or x squared minus 4 squared. You okay? All right, so as a first derivative, now, if you wanted to figure out monotony, relative extrema, this is your place. You find here zeros at the top, zeros at the bottom, put them in a line, and do your business. Okay? Now, we don't want that. We're looking for concavity, so we have to go deeper. We need to look at the second derivative now. So, to do the second derivative, what do we need to do? Quotient rule again. You could bring this guy to the top and then use a product rule, but then it's product rule together with the chain rule with the negative exponent, and I don't want to deal with that, okay? So I'm just going to do quotient rule again. So derivative of the top, negative 10 times the bottom minus the top times the derivative of the bottom. What's the derivative of the bottom? Little chain rule here. What is it? 2 times x squared minus 4 times the derivative of the inside, which is 2x. You understand this? That's a general power rule. All of this divided by the bottom square. So square minus 4 to the 4th power because of the square. Yes? Okay, now cleaning up time. All right, so let's see, what are the stuff that I can factor out from here before I start multiplying things? Well, there's an x minus 4 here. There's an x minus 4 here. I can take that out. There is a negative 10 in here, and there is a negative 10 in here that I could also take out. Do you understand this? I'm going to factor that. So I'm going to take out negative 10 times x squared minus 4. What's left? Let's see, from the first term, what's left if I take this out? Take out the negative 10, take out x squared minus 4, what's left?
X squared minus 4.
Another x squared minus 4. Minus, so from this thing over here, I'm taking out negative 10 and this guy. So what's left? A 4x squared. And the reason why I did it like that instead of multiplying everything and so on is because I saw that I could take out x squared minus 4 and then it would cancel with this one down here to lower the power. Okay? Because if you multiply everything, then you need to deal with factoring the top to see if you could simplify more. And then that would be like a huge polynomial in the top that you will need to factor. Well, here you already have the factoring for free, basically. Okay? All right, so questions up to this step? Okay, so this guy cancel with this one, give me a 3 here, And then here we're going to have negative 3x squared minus 4. And then, remember, if you have a rational expression, you need to factor top and bottom as much as you can. So here I'm going to take out the negative. So that would be a 10. Now, the top, it may look a little bit unconventional, but we can factor it. No, we can't. Never mind. That's a 3x squared plus 4. Now, the bottom we can factor. What is it? That's an x plus 2, x minus 2. But remember, that's to the cube. So we need to cube each factor. This is our second derivative. This is as simple as it gets for the second derivative. We cannot simplify this more. Now, we analyze it, okay? We need to analyze the zeros. Questions up to here? All right, so sine for the second derivative. So we need the zeros. Do we have any zeros here? It's a fraction. The zeros of a fraction come from the top. Is the top 0 at some point? No, it's not. That's a 3x squared plus 4. That's always positive.
So it's
Yes? This is a 3x squared plus 4. This is always positive. You understand this? So we don't have any 0 coming from here.
So it's undefined. No, not.
And then values that make it undefined. Do we have any values that make the second derivative undefined? Negative 2 and positive 2. Those are the zeros at the bottom. Now, I want you to understand that these guys were not even in the domain to begin with. Okay? So, are we going to have inflection points? We are not going to have inflection points. We'll be able to say something about concavity, but no inflection points here. Okay? So, get ready. Zeros of the function, we don't have it. Undefined, we have two guys. What's happening at these points, by the way? We have vertical asymptotes at those points. Look at the original function. It's a rational function. Zeros at the bottom is your vertical asymptotes, right? Plus or minus 2 are vertical asymptotes. Okay, so let's look at the sign of the second derivative. The top is always positive, so we only need to worry about the bottom, okay? The sign of the bottom determines the sign of the whole thing. So we pick something here, negative 3. So as a negative, because we're cubing, so still a negative, and then times negative. So as a positive, then we pick 0. That's going to be positive times negative. That's a negative. Then we pick 3. So positive times positive. So as a positive. So what do we have here? Concave up, concave down, concave up. And we have no inflection points. No inflection points, since x equals negative 2 and 2 are not even in the domain. Even if you see the concavity changing around these points, they're not even in the domain, so we don't care about it. You okay with this? For example, if you were to think about the graph of this function, how this function looks like, you can do this with your Picard knowledge. So here is negative 2, here is positive 2. You have your vertical asymptotes. What's the horizontal asymptote for this function? What's the horizontal asymptote? We're doing this on Wednesday, so you need to remember all these things. What's the horizontal asymptote? It's 1, or in the limit at infinity. Ratio of leading coefficient, because degrees are the same. So it's 1. So here we have 1. Let's put it over here. Okay, now to the left of negative 2, the function has to be concave up. If you do a sign analysis of the function itself, you should get that it's positive. Therefore, you're going to have a behavior like this. Between negative 2 and 2 is concave down. And then what's the 0? What's the y-intercept? It has no zeros. It's never going to touch the x-axis. And when you plug in 0, you get negative a quarter. So here is negative 1 over 4. And that's an even function also. So This is going to look on this side, concave down up to here. Now the rest, copy and paste by symmetry. That's the graph of that function, and then we can see the concavity right there. Concave up, concave down, concave up again. No inflection points. Do you understand this? We're doing this on Wednesday more carefully, okay? And for example, what can you say about the derivative of this function? We didn't analyze the sign of the derivative, but now you have the picture. So what happens from 0 to negative 2? Is the derivative positive or negative? It's positive. What happens from negative 2 to 0?
It turns negative.
It's positive, going up. Yes? Then what happens from 0 to 2 for the derivative? It's going to be negative. And from 2 to infinity?
Positive.
It's going to be negative. It's decreasing. The function is going down. I'm talking about first derivative.
Oh,
Okay? We're going to do it backwards, of course. You're going to have all of that information, and then you put it together to produce a picture. That's what we're doing on Wednesday. Okay? We're going to be putting all of that together to produce pictures. Okay, so I'm not going to do these two examples. Maybe we do it on Wednesday, and then we try sketching these functions and so on. Okay? I'm going to use this for sketching, so I would rather do an application problem now than spend time on this because it's just going to be the same as the same. Okay? The algebra could be slightly different, then it's a little bit trick, but we already discussed on trick today. Okay? So think about this on your own. On Wednesday, we discuss. So I'm going to let you try this on your own. But, second derivative test. The second derivative test is super easy. The thing is that you have homework on this. So let me just tell you what it is. This is another way of finding maximum and minimum. Okay? So let's say that you already know that you have a critical number, which could be a maximum or a minimum, right? That's a candidate for maximum or minimum. And let's say that you find the second derivative. You want to know where is a maximum or minimum. And if you want to look at the second derivative, then that means that this number better be defined for the second derivative. So it has to be stationary. Okay? It cannot be a point at which the derivative is undefined, because then forget about talking about second derivative. Yes? If you want to look at second derivative, it has to be a stationary critical point. Now, let's say that you have yourself a stationary critical point. Okay? Then if this is going to be a maximum, for example, if it's going to be a maximum, so let x equals c be a stationary critical point. So i.e. f prime of c is 0. Okay? So let's say that we know this. Now, it is a candidate for relative extrema. So if it is a relative max, then how does the function look like at this point? If it's a relative max, what will be the shape? Right? So it should be something like this. Because remember, you're going to have your horizontal tangent line here, nicely, and then if it's a relative max, it's going to look like that. Yes? What's the concavity at that point? So over here, if you look at a little interval, what concavity do we have? Concave down. So what can we say about the second derivative on that little interval? It's going to be positive or negative? Negative. So if I were to plug in my second derivative, to plug in these numbers into a second derivative, I'm expecting to get a negative number. You understand this? So instead of analyzing the sign of the first derivative to see where it's a maximum or minimum, that's what the first derivative test tells you. What you could do is sometimes it's very easy to keep going, take the second derivative, and then plug in. You get a negative number, it's a max. Okay? So if it's a relative maximum, then second derivative is negative. And then similarly, if it would have been a relative mean, then what was the picture? It would look like something like this. Right? With your tangent line down there. Yes? What's the concavity there? This is concave up. So that means that if I find my second derivative and I plug in c, what am I expecting to get? A positive number. This is called the second derivative test. Okay? The second derivative test says if you have a stationary critical point, and then when you plug it into a second derivative, if it's negative, you have yourself a maximum. If it's positive, you have to solve for minimum. You understand this? That's called second derivative test.
Oh, right, now what's going on?
Just gonna write it down. So the second derivative test, and you have questions like this in the homework, so now you know how to answer. Second derivative test. So let x equal c be a stationary point of f, so i.e. f prime of c is equal to 0, then if f, the second derivative of letter c is a negative number, then f has a relative maximum at c. If the derivative at c is positive, then f has a relative mean at x equals c. Okay. Now, if you have x equal to 0, then this is inconclusive. Okay. It could be a relative extrema, or maybe it is an inflection point. We don't know. So what do you do if you get second derivative equal to 0? Go back to first derivative test. I always like to do first derivative test because that always works regardless. Okay. But second derivative test is nice computationally because you don't have to look at signs. I mean, you don't have to do inequalities. You just compute, plug in, and then see what you get. But if you get 0, then you have no choice. If it is equal to 0, then cannot conclude. Cannot conclude anything. So use the first derivative test. Okay? That's a statement of the second derivative test. Again, if you forget which one is the maximum, which one is the minimum, think about x squared, negative x squared. So x squared, what does it have? A maximum or a minimum? A minimum. What do you know about the second derivative at 0? It's positive. So second derivative is positive, minimum. Negative x squared, what does it have? Maximum or minimum? Maximum. What's the second derivative? Negative. So second derivative negative at the point, give you a maximum. Okay? That will be your analysis. So I guess we cannot